Alright guys, so to pick up where we left off on the discussion of complex power, I wanted to go over a couple of examples. And these examples are actually coming directly out of the labs that we would have done with the lab volt machines. Now, if we do get to come back and finish up this semester, which so far we anticipate that's going to happen, we'll be able to go back and revisit these. But these problems that I derived for the lab are actually really good examples on how to actually not only do calculations with complex power, but also about furthering diving into the sinusoidal steady state analysis methods that we've been working with up until this point. So before we get started, I want to actually just talk about a couple of ways that we can actually re-look at the equations for the complex power. Now, everything that we're doing from here on out is all in RMS. And remember that RMS, the equation VRMS times IRMS conjugate, that is equal to 1/2 V times I conjugate. But there's different variations of these equations. Number one, the first variation, just in the same way that we could easily take Ohm's law, or even the impedance version of Ohm's law, and then just basically re-manipulate Ohm's law into all voltage or all impedance, or all current and all impedance. So here, VRMS, the magnitude of RMS would be squared divided by the conjugate of the total impedance, or IRMS conjugated, the magnitude of it, not conjugate, squared times the impedance themselves. And one thing that we're going to see later on is that, in fact, actually the impedance holds the phase angle of the complex power, which is a very, very cool concept here. But we're going to start off really small, and then we're actually going to go over and essentially do a very, very similar problem. First one, we're going to be looking at the power supplied to the load, and then we're going to look at the power that's actually being supplied by the source as far as total complex power. So for this one, we actually wanted to find basically the power, complex power delivered to this load. Now this load is in fact made up of two parallel branches in which we have 200 ohm resistor and then negative J600 for capacitor's impedance, and then negative J300 and then 600 ohms worth of resistance. Now these are the actual values that we would calculate if we utilize the lab volt machines, and we would get these directly from taking 377 radians per second and then utilizing the values of capacitance in order to actually calculate these values of impedance. But if we take the load itself, we would actually go ahead and combine these in terms of their parallel equivalents, in which we would actually get for the parallel equivalence of the load, we would have 200 minus J600 in parallel with 600 minus J300. And that actually comes out to be equal to an equivalence of 227.58 minus J268.97 ohms. And so from here, we can go through and simply not only perform voltage division. In order to find the voltage across that impedance, we can actually go ahead and garner the current that's flowing out of that source. And by taking the current that's going to flow through that equivalence and the voltage across it, we can actually know the total complex power that's actually being supplied to that load itself. And so IX, once we actually have broken this circuit down into its apparently series equivalents, IX is just equal to 60 at an angle of 0 degrees divided by 300 plus 227.58 minus J268.97. And from there we get a complex current of 0.1013 and an angle of 27.013 amps. So to find the voltage between these 2 points or across that load itself, all we have to do is just simple voltage division. 60 at an angle of 0 degrees. Multiply that by the equivalent impedance, 227.58 minus J268.97 over 300 plus 227.58 minus J268.97. And that comes out to give us a value of 35.7 at an angle of negative 22.75 degrees. And one thing to note here, guys, is that we do in fact have a more capacitive natured load here. And so by that notion, that current should lead the voltage in that load. In fact, we do see that sure enough, the current's angle is 27.013 degrees. And the voltage's phase angle is negative 22.75 degrees. So in fact, actually, we do see that the current is actually 100% leading that voltage for sure, rendering that and also proving that it is a capacitive load in nature. So for the complex power in that load, all we have to do is just say S is equal to VRMS times I RMS conjugate, and that's equal to 35.7 at an angle of negative 22.75 degrees, and then multiply that by the conjugate of 0.1013 at an angle of 27.013 degrees. And so that actually causes that phase angle of 27.013 to turn into negative, and then that ends up giving us a value of 3.62 at an angle of negative 49.76 degrees volt amperes. But if we go ahead and convert that into the polar form, we can actually see the real and reactive portions. Now, the real portion is actually 2.3385 watts, while the reactive portion of that power is in fact actually equal to negative 2.7633 var. Note though that once again we have a capacitive load, and with that capacitive load we see that we actually get a negative reactive power, and that's very, very unique to us because we can always determine what type of system that we actually have, even if we actually don't see the schematic. If we see that negative reactive power, then for sure we have a capacitive system, or usually resistive capacitive system. But anytime we have a positive reactive power, that is indicative of an inductive system, for sure. So, once again, watts, var, the total complex power is in fact actually volt amperes. But you know, if we go back, there's another way that we could also think about this in terms of that current, and just even compare it even to the source. The source here was 60 at an angle of 0 degrees. Now, if we look at the current is still leading by 27.013 degrees. So once again, anytime the current's leading the voltage, we see that as being capacitive in nature. Anytime we see that current lagging behind the voltage, we see that as inductive in nature. And this is the part where I always just want to look at everybody and say, does anybody have any questions? But since no one's here, in fact, actually, a couple of people walked by earlier and thought I was just talking to the room blankly until they saw the camera. Let's do another problem. And I'm going to get out of here because I'm starving. All right. Time to move it over. All right. So, problem number 2. And in this one, we're actually going to look for, oh man. This one, we're actually going to look for, there we go. We're going to look for the complex power that's actually being supplied by the source. And so for this problem, we actually had 3 parallel branches in which we not only had capacitors in 2 of the branches, but also we had an inductor. So once again, if we want to look at the power supplied by the source, now this is RMS, just in the same way that one was RMS. Allows us for ease of calculation, and also these are based off the lab volt machines, which everything that we're utilizing there is also in terms of RMS. But in order for us to actually find the complex power being supplied by the source, we need to find the current first. But we're also going to see that we sometimes don't even need the current in order to find that complex power. So all we do is take 40 minus J 111.1 in parallel, 25 minus J 74.07, and then also in parallel with 12 plus J 0.9, we get an equivalent impedance of 10.87 minus J 1.673 ohms. From there, we can actually break down the circuit into a series loop, piece of cake here. Find IX. We find IX, we got 30, that's in series with 10.87, as well as minus J 1.673 ohms. So the source current that we actually get, which obviously that's an RMS as well, is equal to 25 minus minus 35 degrees, its phase angle, over 30 plus 10.87 minus J 1.673. And that gives us a current value of 0.6112 and an angle of negative 32.66 degrees amps. So from here we can go through and easily find the complex power from the source, 25 at an angle of negative 35 degrees, and then here multiplied by the conjugate of 0.6112 at an angle of negative 32.66 degrees. That conjugate actually renders a very, very, very small value here in terms of the phase difference. So here we get 15.28 at an angle of negative 2.34 degrees volt amperes. And guys, what this is actually really indicative of, considering the fact that we are looking at this type of system here, is in fact actually, once again, if we consider that this is mostly a capacitive system, this current is in fact actually leading that voltage for sure. Definitely leading that voltage, therefore rendering essentially that type of phase difference in which the current its phase angle is above the voltage's phase angle. Now, I promised that we were going to come back and look at this form of the equation that we had over on to the right, which may have not, I don't think it's actually in the camera's viewpoint anymore, but sometimes we actually don't even need to concern ourselves with the current at all. We can just concern ourselves directly with the impedance. And in this case, we already have the source voltage. We also have the total impedance. And so if we look here, we actually get VRMS squared, or essentially the magnitude of that voltage squared divided by the conjugate of the total impedance within the system. And so we take the magnitude of 25 at an angle of negative 35 degrees, which is just 25 squared, over 30 plus 10.8 minus J 1.673. And that also, guys, that gives us a value of 15.28 at an angle of negative 2.34 degrees volt amperes. And what that means is that, sure enough, as promised earlier, that phase angle is actually conserved within the impedance itself. All right. Just as before, if you guys have questions on this, you're going to have homework that you're going to work on to actually work through these problems and also get experience with this. And if you have any questions, please contact me.